Welcome to the first Learning Machine seminar series talk. So this is going to be an ongoing series. We have a few more talks scheduled. You can look at the seminar series website. I'm very excited to have for our inaugural first talk Ray Mooney from UT Austin. So Ray is really a leader in AI and NLP, and I think that sometimes this term used kind of in exaggeration, but Ray's been around for this year, which will be 30 years, right? Doing research in AI, NLP, and machine learning, and kind of like in the last few years, branching up to vision and now robotics. And what I really like about Ray's work, and I think we're going to see a lot of it today, is that there's kind of like a complete lack of fear. So people always talk about this grand goals that we need to solve and we need to try to build, but let's first do something like a step in the direction because they are not really feasible. Ray is kind of like charging forward and going and working with real robots and video, and that's been always exciting to me. So I'll let Ray start.
Thanks, Joe, for the nice introduction. I'm happy to be here in your new building with the nice view of the skyline behind me. So, as Joe said, I'm going to talk today about, this is actually my first time to give a normal university talk on our robot language stuff. So I'm happy, hopefully this will go reasonably well. There's sort of 4 conference talks in here, so I'm a little afraid I've tried to jam too much, but hopefully not. So, I titled it Robots That Learn Grounded Language Through Interactive Dialogue. And of course, this is joint work with a lot of people. First and foremost, my 2 PhD students, Jesse Thomason and Aishwarya Adamakumar, but also a postdoc that just actually left UT, now started as a faculty member at Tufts, JIVCO. My robotics fellow faculty member, Peter Stone, another former postdoc, Shiki, current postdoc, Justin, and undergraduate student, actually, Max. So it was a pretty large team of people that worked on various aspects, but Jesse and Aishwarya are the main 2 people behind this. So as Yoav said, a topic that I've been interested in a very long time is grounded language. And I call language grounding connecting language to perception and action. So traditionally, most work in natural language processing tries to understand language by just dealing with text and representing meanings of words and sentences in some sort of symbolic representation that really doesn't have any connection to reality. And I've really been a believer, even since I was a grad student in the 80s, that to truly understand natural language, we need to understand the connection between language and the world, in particular the way that an intelligent agent perceives the world and acts in the world. So we really, to get the real meaning of language, we need to understand the connection between language and perception and action. So I've done a variety of different work related to this in simulated worlds, giving robots instructions in simulated worlds, sports casting, language and vision, producing video captioning. And most recently, I've been working with real dialogue with real robots. And another issue we're trying to address is, where do you collect the training data from? So the traditional way we build NLP systems these days, including robotic ones, is to require large amounts of pre-assembled, manually labeled training data, where you have people annotate sentences with all sorts of, syntactic, semantic information. And that's very laborious, and it's also it risks not reflecting the real actual needs of the end application. So ideally, we'd like to develop a robot that sort of you throw it out into the world and it learns to understand language by interacting with people and learning from its natural dialogue with actual human users. So we've tried to work towards a system. Now, we certainly first bootstrap it to understand some amount of language to start with, because people are going to get very frustrated if you throw a completely, ignorant robot at them. But we try to give it just minimal training to start with, and then just put it out into the world, have it interact with people, and learn from its natural dialogue interaction with actual human users. So this is an example of the robot we've been playing with. So like I said, the robot side of things is mainly nailed down by my robotics colleague, Peter Stone. And he's, over quite a few years, has developed these, what he calls segbots, because they're robots based on a segue platform. And it also, a number of them also have these Canova arms on them. And so we'd like to be able to give natural language commands to this as a sort of office robot to give them commands such as go to Alice's offices and get the light mug for the chair, and then have the robot go off and do those tasks. And so there's a number of problems that need to be solved in order to do this. Of course, you need to understand this connection between language and action, so you need to understand the command that the actual human wants the robot to do. You need to understand certain references about how the language connects to the world, and some of that might come from world knowledge that you have about your office environment. So here, when I say Alice's office, I need to know, well, what office is that? So I assume I have a knowledge base of the residents of the building and what offices that they're in that I can ground that in. And here I have the chair. Where here, this doesn't mean the physical chair in the world. This ideas here this example also tries to illustrate the ambiguity of language, where that might refer to the chair of the department. So I need to ground that in, where the chair's office is. And then we do have this actual perceptual grounding going on, like the light mug, where we need to identify the reference of these natural language descriptions as actual objects in the world by connecting it to the actual robot perception of those. And again, there's ambiguity involved there, because light, in this case, could mean light in weight or light in color. So we're trying to build a system that can handle all of these things together and learn the variety of knowledge that it needs to do this from interaction with users. So as I said, I'm going to talk about sort of 4 parts of this project that appeared in 4 different conference papers. So the first part I'm going to talk about was a paper that's a couple years old. It appeared at ISpy a couple of years ago on learning to interpret natural language commands through human-robot dialogue. And this is combining areas of sort of, commanding robots, having dialogue, doing that over dialogue, and using, a problem that I've worked on that Yoav's also worked on a lot, which is semantic parsing. And put these all 3 together and learn automatically a semantic parser that engages from dialogue. So if you're interested in more details, that's an ISpy paper from a couple of years ago. So, dialogue, people have been working on dialogue systems for several decades now. Most of them have been on phone systems. So we were talking earlier about that Yoav's done some work with this ADIS corpus that goes pretty far back, the airline travel information. So there's a lot of problems like that where people have done dialogue. There's relatively little work with dialogue with robots, which I think is another interesting connection, is the connection between dialogue systems and robotics. Because most dialogue systems have been on these sort of phone information system sort of platform, where you have some user, they put in some text, you have some sort of natural language understanding that produces some sort of abstract representation of the meaning of the user's utterance. And then the system keeps track of the dialogue, where over time it's trying to build up a representation of the intention of the user, right? What the user wants. Like for the ADIS problem, it's what flight they want to book, to what time and what date to what place. And then the system has a policy of how it engages in that dialogue, usually called the dialogue policy, which looks at its current understanding of its understanding of the user's intent, and then comes up maybe with questions, clarification questions that drive the dialogue towards a conclusion about what it is exactly that the user wants. So we're trying to say, hey, let's connect this idea of a dialogue system to a robot. Because it's hard to just say one thing and have the robot immediately understand what you want. Maybe it has to engage you in some clarification questions until it finally understands what you want. So, but then eventually, when the dialogue state does reach a convergence and the system is confident that it has a firm understanding of what the user wants, then it can actually send that command out to a robot. And there's where my robotics colleagues take over, and we produce a formal command representation that we have the robot actually execute the command that we finally decided that the user wants. So one big part of this is the problem of semantic parsing, which I've worked on a lot, Yoav has worked on a lot, where you take a sentence and you want to produce a sort of logical, formal meaning representation for that sentence. So here I put this example here, and a typical framework uses lambda calculus, which is what we've been using for this task. And I won't go through the details of this, but this is sort of a formal logical representation of that command that we could then give to the robot and it could actually try to execute. So it says, go to the place that's an office that's owned by Alice and deliver the thing which is both light and is a mug and deliver that to Bob. Okay. So part of this work was very much inspired. It's nice to give this talk here because a good part of this work was inspired by some previous work that Yoav did with Luke from 2011 on how to learn semantic parsers from dialogue information. And they originally did it as in this information, online phone information, so ATIS, airline travel information domain. So we were inspired by that idea, but we wanted to apply it to robot dialogue. And the idea is when the system engages the user in this clarification dialogue, when it finally it understands what it thinks the user meant, then it can pair its final understanding with the original utterance that the human user used to describe that and automatically create training examples. So the big problem with learning semantic parsing traditionally is you need supervised data. You need sentences paired with logical forms. And, you know, not ordinary users have a really hard time typing in lambda calculus expressions, formally defining the meaning of natural language utterances. So here we're going to engage the user in a normal natural language dialogue, and through that it's going to automatically construct formal representations that can be used to train the semantic parser. So to give an example of how this works, we've done experiments both on the real robot and in simulation on Mechanical Turk. So a lot of the data, it's much easier, of course, to collect larger amounts of data online using Mechanical Turk. So here's an example of a conversation. So the way we tell people a task is we give them a database of people, and we give those people titles and nicknames and things, and we tell them, you know, use a lot of variety of ways to refer to these people. And so we don't bias them in terms of the language they use to describe the objects we want them to deliver to particular people. We give them pictures of a set of objects. And then we tell them, you know, get the robot to deliver item number 3 to some particular person. So here it says, you know, so we tell the user here, Dave Daniel wants item in slot 5. And so the robot says, how can I help? The user says, the user here is a little naive. They actually think they can refer to things by the slot. Of course, we tried to instruct them to tell him, you know, do a linguistic description of that item. But he initially just says, bring item in slot 5 to Dave Daniel. He says, who should I bring something to? Dave Daniel. What action do you want me to take? 5. What should I take to Dave Daniel? A calendar. Do people understand why it doesn't get it at that point? It actually knows the term calendar, but what's wrong with this expression? Misspelled. It's misspelled, so it still doesn't understand. It says, I'm sorry, what should I bring? A day planner. It still doesn't know. I'm sorry, they couldn't pinpoint what you meant. What should I bring to Dave Daniel? Calendar. Finally, they say it in the term that it understands and they spell it correctly. And then it says, oh, you want me to bring the calendar? Yes, I thought so. Now, from all of this back and forth, let's automatically build training data.
So slot 5 doesn't work here. There is no notion of 1, 2, 3, 4, 5 in the...
No, the semantic parser doesn't know that. What the heck just happened? Okay, so the first training example it builds is it builds up the initial thing, please bring item in slot 5 to Dave now, to its final representation of the entire sentence. But it also, suddenly my clicker stopped working. That's not good. It also comes up with a training example pair from a calendar to the misspelled calendar to the calendar, and a day planner to the calendar. So from that one clarification dialogue, it automatically constructs 3 training pairs. The whole sentence, and then a calendar, misspelled to calendar, and a date planner to calendar, and it gives that as training. Now, the next time anybody uses those expressions, it'll be able to understand them because it's automatically built training data and retrained the parser to do that. So that's the idea of building up training examples automatically from dialogues. So like I said, we ran a number of experiments to evaluate this whole approach, and the main hypothesis we're trying to test here is that performing incremental retraining of the parser with this sort of training data obtained from these clarification dialogues will eventually make the system more and more robust and be able to understand more and more things. So we tested that both on a larger scale experiment online using Mechanical Turk with more users but less realistic interaction. And then we actually tested on this real SegBot robot with the fewer users and more natural interactions with a real robot. Okay, now it's working again. So in the Mechanical Turk, we had 4 batches of about 100 users each, and then we retrained after every batch. When you're doing this online learning with Turk, it's hard to sort of train after every user because they're all using the system at the same time. So we batch it and we do 100 users and then retrain another 100 users and retrain and so forth. And then we measure performance on an independent set of test goals. So when the test goals are guaranteed to be different commands than anybody during training. So you're delivering something new to somebody new. I mean, you've maybe seen the person before and the object before, but you've never seen delivering that person to that object. So there are 2 types of goals in this simple little robot environment. Navigation, you just tell the robot to go someplace, and the other one is delivery, deliver some item to some person, using that sort of framework that I just showed you, the interface that I showed you on the previous slides. I don't know why that clicker's being so iffy. So one way we evaluated it is we asked them a survey at the end of their use of the experiment. Did the robot understand you? And we do that in batch 0. It has I said we boot up an initial semantic parser from just a handful of training examples so it understands something. And then as it goes through batches, you can see it's learning because the user, actually does believe in later batches that having learned from those earlier batches and the clarification dialogue with those longer conversations early on, it's learned and it gets to understand people better over time. And then we also looked at the length of the dialogues, because you'd like to think over time by having to engage in less clarification, the system converges on its understanding of the user more quickly. Now, it turns out for the navigation task, there's really only one argument there, which is where to go. And it didn't really get better there. In fact, the dialogues get a little bit longer. It gets more accurate, but it sort of engages in better clarification. But you can see on the delivery task, the dialogues get shorter. Because initially, they're that crazy sort of back and forth, the way I showed you an example. But by the end, it's seen enough users asking for those various items. It's learned the way that people refer to those items and those people and the command of delivery, and it gets better over time. And the dialogues actually get shorter. Okay, then we did an experiment, like I said, with the real robot. This is much smaller scale because running experiments with real robots in the lab is, of course, a lot more pragmatically difficult. So we had 10 users use the baseline system with no additional training. And then we had the robot roam the office for 4 days. It had 34 conversations with users in the office, ended with those training goals. Again, it had the same task, navigation and delivery. And then it retrained just once after that 4 days of interaction. And then we gave a final test, 10 users retrained this with the retrained system, and to see how much better it was. So here's just success, because we allowed the user, if they eventually got frustrated and couldn't get the robot to do what they want, they could give up. So delivery, navigation is not that hard because there's just one thing, so we didn't really see an improvement on that. But we did see dramatic improvement on the delivery task. That initially, with the initial very small training set that was the bootstrap system we started with, it just got 20% accomplished, and now by the end it was getting 60% after 4 days of just talking to users. And we also gave it one of these surveys about the robot understood me, and not surprisingly, compared to the original group, many more people thought that the robot understood it after it had a conversation with people for 4 days and learned from that interaction. Okay? So that was the experiments we ran a couple of years ago, just demonstrating that you can learn, robots can learn to understand. Oh, okay.
Can we ask a clarifying question?
Sure, Claire.
Hi, actually, Marseille should say hello. Marseille, say hello.
That's our dog. Yeah.
So, just a quick question. Why only 34 conversations in 4 days? I would have guessed you could get a ton.
Well, this is just up in our lab, right? So this is just people who we could convince to, people who happen to be students who were wandering around the lab that we could convince to have conversations with the robots.
Okay.
Not everybody, they want to get their homework done or something. They weren't willing to talk to a robot who doesn't understand it most of the time.
And these were kind of curated question tests, or did the users do what you asked them to do?
They were told the space of tasks that you could ask. Obviously, they weren't told exactly how to say it, but they were told the range of tasks. Exactly what we told them, I don't remember, but they were told the type of task that you could ask it to do.
Another question?
Yeah.
Hey, so have you looked at initiative at all? Can the robot take the initiative and actually sort of guide the user in any sort of way?
So we'll get into this here, but the dialogue policy here is fixed. It was just a hand-coded policy that Jesse put together, where it had various thresholds on if it understood something pretty well, then it would just ask confirmation. Otherwise, it would ask if it didn't understand how a particular slot was filled. So there's a fixed dialogue policy, and we're going to get to changing and learning a better dialogue policy. That's actually the next part. So it's a very simple dialogue policy that it's engaged in right here. Yeah.
Is it the same users for the different batches?
No, there's new users every batch. I mean, I guess it's possible on Turk that some users had come back, but it certainly was intended to be new users.
Because the users can adapt to the system.
Yeah, we certainly didn't want to do that. So I don't even know if you can on Turk easily control to make sure, because they could come up with other Sybil accounts or something, right? So we certainly tried to make them new users. Yeah.
Did the users receive any instruction on how to communicate with the robot?
Well, again, I'd have to, you know, obviously when you do Turkic experiments, you have an introductory little document that tells the person about the hit and all this stuff. And so we definitely had something and told them some things about that. I don't have the actual text with me that we told them. But basically, we just tried to tell them, you know, we tried to get them to vary their language and talk about how to deliver it and who to deliver it to and what to deliver it to, use as much variety in their language as possible. We tried to encourage them not to be too scripted. Okay. Yeah.
Did you come up with a good way to deal with noise? So like if it was like, it didn't understand calendar and then they said, why didn't you understand me? And then that would be used as an example.
So I mean, again, this process could pair together things that really don't mean the same thing. There's certainly a possibility. But then again, you know, all semantic parser learning algorithms have some overfitting prevention in the underlying learning. So hopefully a little bit of noise in the training data is not going to screw up the training too much. Because, you know, we actually use I think this version actually used the actual SPF, which is Yoav's, you know, semantic parsing learning framework. And, you know, you have various things in there that hopefully prevent overfitting if there's a little bit of noise in the training data.
That's a very good tactic.
Okay, so the next time I want to talk about is a paper we presented at EACL this past spring on integrated learning of dialogue strategies and semantic parsing. So as I said, the current system that I mentioned before had a very fixed, simple, hand-coded dialogue policy. One thing that worked out nice with my student Jesse Thomason, who works on this, he actually came as an undergraduate from Pitt, where he worked with Diane Littman on actual dialogue systems as an undergrad. He actually published a conference paper as an undergrad at NACL based on his work on dialogue with Diane. So he was a great student to recruit to this project because he had some pretty good background. Because I'm new to dialogue. I'm not a dialogue person. So it was great to have someone who was actually trained by a real dialogue person. Diane worked on this. So it was a decent hand-coded policy. This is a student who, you know, did real dialogue work before he came to UT. But I don't know how many of you know this, but there's a whole big area within dialogue, actually started by Diane Littman back when she was at AT&T Labs in the 90s, on using reinforcement learning to learn better dialogue policies from experience, where they did this on these phone systems, right, where the system gets rewarded when a user actually accomplishes their goal on the information system, and then it gets negative reward for every question it asks, so it sort of encourages it to, you know, wrap up the dialogue quickly. And there's a whole long tradition dating back to the 90s of using reinforcement learning to learn better strategies for engaging in dialogue. So we wanted to exploit that. But I was talking to Elaine here earlier that there's these two communities within NLP. The dialogue community and the semantic parsing community. Historically, they have had no connection to each other. And I'm a big believer in bringing communities together. So in this work, we're trying to bring together these two communities. Because, you know, so Yoav started this approach to learning semantic parsers from dialogue. We followed it up in robotics. But you can also learn better dialogue policies from engaging in dialogue. So I asked a new student that just had started working with me the year before, Aishwarya, can't we do both of these? Can't we learn both better dialogue policy and better semantic parsing by just engaging users in back and forth dialogue? So this is what we tried to do. So again, there's a lot of work on how you treat dialogue policy learning as a partially observable Markov decision process and learn a better policy using reinforcement learning. And it basically obeys this sort of picture where it has a basic sort of reinforcement learning framework where you have an environment and then it's partially observable because then you don't get to see the whole state, you observe something from the environment which then changes the agent's belief about the world, and then that causes them to do some action which then changes the world. So it's sort of a standard partially observable Markov decision process. And like I said, there's a pretty long tradition of treating these clarification dialogues as POM-TPs, where the states, what you're trying to figure out, of course, is what does the user want? What delivery task do they want me to do? And so the state is assumed to be sort of the head of the user of what goal they want the robot to accomplish. And that's hidden, of course. That's why it's partially observable. All you see as observation is language that the user generates about their state of mind. And then the actions are the robot can do various dialogue actions, mainly confirming, saying, do you want me, you want me to deliver a calendar to David Jones or whatever. Or maybe requesting, what do you want me to deliver to David Jones? Or who do you want me to deliver the calendar to? So there are various actions that the system can engage in. And the idea is you can then train this sort of model using reinforcement learning so that, like I said, you get a positive reward when you successfully accomplish a user's goal, and you get negative reward every time you have another utterance. And then you run reinforcement learning to maximize reward and hopefully learn a better policy for when to ask questions and what questions to ask to make the dialogues more successful. The challenging thing is, like I said, all the work before on dialogue strategy learning assumes a fixed semantic interpreter. And the thing that changes for us is the semantic parser is changing. And so what we observe from the environment is changing, because what we're observing is the output of the semantic parser. We take the utterance that the user says, we semantically parse it, and we take that as the observation of the state. But that environment is changing because the semantic parser is learning over time. And this is something that reinforcement learning algorithms don't like at all. It's called a non-stationary environment. All RL algorithms basically assume the world, the way the world behaves isn't changing. But here it is because I'm changing the semantic parser. So how do we integrate both of these? So one thing we tried to do is use the latest, best reinforcement learning technology that's at least as insensitive to non-stationary environments as possible. So having read the literature, Aishwarya was a great student who recruited this project too. She did some work as an undergrad at IIT in India doing reinforcement learning. So she had some nice background in RL. She also took Peter Stone's class on reinforcement learning. So I had some good background students and she decided to use this thing called Kalman temporal differences, KTD-Q learning from Geist and Pedquin. Don't ask me about this because I am not an RL person. A guy who's done a lot of work on RL for dialogue recently is this guy Steve Young at the University of Cambridge. So we adopted his latest work on dialogue state tracking. Well, it's not the latest work, it's pretty old, I guess. And then, so we tried to exploit the latest RL and dialogue strategy learning stuff that's out there. But what we were trying to test was, can we do better by combining parser learning and dialogue learning? Are they better together than either of them is alone? And to do this right, though, you need to make sure that the changes in the parser are seen by the policy learner. So we tried two sorts of approaches. One is sort of what we call full here, which is sort of a total batch learning, where we collect a whole bunch of dialogues online from Mechanical Turk users, and then we, at the end, train a better policy and a better semantic parser on that. The problem is now this policy was based on dialogues that were collected with an outdated semantic parser, and so the dialogue strategy sort of gets out of sync with the semantic parser, and it all sort of goes awry. We'll see this actually doesn't work. So we said, well, we really need to, ideally we would incrementally update both components after every dialogue. But like I said, when you're doing this online with Turkers, it's hard to do that online completely. So we did it in sort of batch incremental style. So we did 4 batches where we engaged in 50 dialogues, then retrained both the parser and the policy, engaged in another 50 dialogues, retrained them both, so that then they maintain in sync. And the dialogue, in the second round, the dialogue policy gets to see the improved semantic parser from the last round. So then we did some final experiments where we measured several metrics. So one is just successful dialogue. Does the user finally finish the task without giving up? And does it perform the correct action? And we told the user what action to have it do, so we know what the correct action is. So we measure the percentage of effective dialogues and also the average dialogue length. So you would hope a good policy and a good semantic parser would also decrease the length of the dialogues over time. And then we did one of these sort of surveys where we asked the user if the robot understood them. So here's the stats on dialogue success. You can see this is just parser learning. This is just dialogue learning. This is this batch where we train them both at the end. And then this is where we integrate and do that batch incremental where we train them both in unison so they can keep up with each other. And not surprisingly, our hypothesis worked out that that does the best. The interesting thing is the parser learning dialogue full actually doesn't even do as well as parser learning alone. So actually, by not keeping the dialogue policy and the parser sort of in sync with each other, the dialogue policy learning actually hurts. It would have been better not to learn a better policy and just do parser learning alone. So it's really critical to do those updates. So the parser learning overall helps more than dialogue learning, but dialogue learning alone also helps. So it was able to learn a better policy than the simple hand-coded policy that Jesse originally put into the system. And dialogue length, a similar sort of thing. By doing them jointly together and integrating the learning in this batch-wise fashion, we got the shortest final dialogues. And again, actually doing the full approach without, it actually makes things worse. And then the survey shows the same thing, that the integrated system that does this batch-wise update to both policies does the best. Okay? So then to move on to the, I don't know, I guess I could pause there if there's any questions on that part. So again, more details on that are in the EACL paper from this past spring. Okay. The next thing I'd like to talk about gets to that issue of perceptual grounding. Remember, I put in the thing, the light mug sort of problem. So we had a paper at ISpy last year called Learning Multimodal Grounded Linguistic Semantics by Playing ISpy. So here we're trying to combine multimodal perception, not just vision, but other robotic senses, how to ground the meaning of language, not just in vision. There's been a lot of work on language and vision over the last decade. I've done a fair bit of it myself. But do this in the context of human-robot interaction. So the thing we came up with is we have users play this sort of ISpy game with the computer. So we have a table, and we put 4 different objects on the table. And we ask the human to describe one of the 4 objects in natural language, and then the robot has to guess what object they're describing. So in this case, the user picks up this Coke can or whatever and describes it as an empty metallic aluminum container. And then we need to identify which of the 4 objects he's talking about. We also had it play the other way, where the human had to describe an object and the robot had to describe an object and the human had to guess which one it was. And we play it both ways, and through these both games, we try to learn better language grounding. The system hopefully gets better over time at identifying objects based on natural language descriptions. So then eventually the robot makes a guess. So it comes up and then it points to the thing. So here it says, oh, I think you're talking about this. And of course the human says, no, you stupid robot, that's not what I'm talking about. And it goes, okay, my second guess is this what you're talking about? And they say yes, and then it gives it positive training data and it goes and retrains. And hopefully it gets to play this game better over time. So like I said, we want to solve this problem of mapping these natural language expressions like light mugs to objects in the world. That's one of these classic sort of AI problems, usually called the symbol grounding problem. It's this famous paper by Harnett back in '90, saying how he thinks that's an important problem in AI. And of course, particularly in the recent years, there's been a lot of work connecting language to vision. Those are just a few references, a little more connected to the robotics literature, connecting language to robot vision. And there's been a little bit of work connecting to other modalities, such as audio. But we were really interested in connecting language to a wide variety of robotic senses. So we try to ground the meanings of words in multimodal robotic sensory data that goes beyond just vision. And then we produce a pretty large, complicated multimodal vector. And then we train an object classifier for every word to identify individual words, such as empty and metallic and heavy and soft and things like that, from a bunch of sensory data coming from the robot. And the way that the robot collects this sensory data is it does various activities to the objects. So it grasps it lifts the objects, it lowers them. And all this time it's doing vision, it's collecting video information about this, it's listening. So when it lifts or something, if there's rattles or something, the audio signal actually picks that up. And then when I got some more actions here on the next slide. It also drops it, listens to it when it drops, lifts it, pushes it, maybe if it's soft, it gives. And it collects all this vision, audio, and what robotics we call haptic, which is the resistance in the motors in the arm. So it can learn if things resist when it pushes on them. It can maybe learn a term like soft because when it pushes on it, it gives way, and it senses this through its haptic senses in the robot arm. So we try to ground the meaning of words in all these styles of robotic sensory information. And then we train it by engaging users in this sort of fun, interactive ISpy game. And like I said, sometimes the human describes objects and the robot has to pick it out, or sometimes the robot describes an object and the human has to pick it out. And from all of this, it's gathering training data to train these multimodal classifiers for every word in its vocabulary. Okay, is the framework clear? So here's the set of objects that we use. We did it in sort of 4 folds of 8 objects each. So a bunch of just sort of bottles and cans and stuff of that sort. I don't even know how the students eventually picked all these sort of objects. And we play games with 4 objects at a time. And we wanted to see, does all this extra multimodal sensory data help? So we compared a system that uses vision only, using standard deep, CNN, deep network vision sort of features, compared to using the vision plus all this multimodal data of the haptic and the audio. And we had each participant play 4 games, 2 with each system. They didn't, of course, know whether they were playing with the vision system or the multimodal system. And so each system saw all 8 objects in the fold. And then we measured game performance. How well do classifiers actually identify the novel objects that people are describing? And there was another team that did some work with ISpy with robots. One thing they did, they used the same objects during training and tests. When we do tests, it's a new set of objects that the system has never seen before during training. We thought that was very important. Because then it's not just memorizing properties of particular objects. So these are then folds where it's learning, again, from each fold for the previous one, so it's sort of hopefully getting better over time. And we compared the average number of guesses to get to the correct object in this 4-item ISpy game, comparing just using vision using the other multimodal senses. And with the multimodality definitely helps. It learns the meanings of these words faster and more accurately from using things other than just vision. It's a little bit weird here that it hops up the error rate. Actually, the number of guesses go up or the accuracy goes down from the second to the third fold. And my student looked at this. There happened to be one freaky object in the test set for the first fold that was really hard, that it hadn't had good experience with the properties of that object, and so it sort of skewed the results on that final fold. Okay, we also then, after the fact, we just took all the data we collected from all those games and ran a leave one object out cross-validation to sort of learn either multimodal or vision predicates from all the data we had collected and then tested on one held out object. And we found that using the multimodal data, you get significantly better accuracy in this leave one object out cross-validation experiment by using more than just vision to identify the meanings of these various words. Okay. Okay, so that wraps up so again, that's an ISpy paper from last year. If you're interested, there are more details on that.
So the robot, when it was playing the ISpy, it was picking up the objects and rattling them?
It did all that in advance. Sorry, I wasn't clear. So before any of the games started, it is offline, played with all of these objects, and collected all this multimodal, multi-sensory data up front with playing with all those objects before the game ever started. Because that's just too much to do during the middle of the game. So that was all precompiled.
So how long did the robot?
Oh God, how long does it take to do all of that? Again, this is where you need the student, because I don't do any real work. I just go out and get the talks about it. But yeah, I mean, it's a lot of work, right? I mean, dealing with real robots, this is why you have grad students, right? So they do all the crap work, so you can just get the glory. So how much time it took to do all that? I don't know. Yeah.
How did the multimodal information help during the ISpy game?
So there are certain words like heavy and empty and full, and so the paper talks about very specific words where certain modalities really help, like heavy. Duh, the haptic senses on the robot arm and it picks it up. It was very useful in identifying heavy or empty or full. So the paper has some more details analyzing very specific words that were helped out by particular sensory data. But yeah, there are definitely certain terms that certain modalities particularly help with. Yeah.
When you were doing the different folds, did you keep the training information from the previous folds, or were they all?
Yeah, it's all compiled.
Okay,
folds. So all previous folds are used as training data on the nth fold. All -1 previous folds are used for training.
Thank you.
Okay.
So is there any other group of researchers that doing the same thing, or you compare your methods with?
Like I said, there's only one other group that did an ISpy type of task, and I really didn't like their method. It was actually from, also a Texas group. It was from a group between UT Arlington and UT University of North Texas, I recall. But they used the same objects during training that they used during tests, and I really didn't like that at all. So I didn't like their whole methodology. So we didn't. I forget the exact method, what they did, but we tried to do a much better experimental methodology. But no, I don't know anyone else who's been ISpy. ISpy is a sort of fun way to play this. And it also engages the users. It's sort of fun. So we bring in students and they play with the robot and they sort of get fun. We'll talk more about that with this part.
Don't they come and take your PhD away if you use your training data for testing?
Yeah. Okay, so our most recent paper on this will be presented this next month at this thing called Coral. I don't know if people know, but there's a new conference called Coral, Conference on Robot Learning, that's going to be on the Google campus like exactly a month from now, or a little like a month to 5 weeks from now, I think. So we just had this paper recently accepted there, where we're adding active learning to this whole framework. So the idea is that, you know, instead of just the user, you know, engaging in this game and the user picking the objects and things, let the system, it's more like the dialogue case, where let the system ask questions while it's engaging in the game. And have it pick good training examples to ask questions about. So have it do active learning engaged in the process in this sort of ISpy scenario, hopefully trying to minimize the amount of training data. You know, so there's a lot of work on active learning. The typical thing to do is usually what's called uncertainty sampling, right? Which is you ask about examples that are close to the decision boundary. And again, there's, you know, a couple of decades of work on active learning. But it's a little bit different in the robotic setting. So what we call what we're doing opportunistic active learning. Because the normal notion of active learning is I can take any unlabeled example and ask a question about it. But when you're in a robotic setting, all the objects in the world are not just lying around for you to ask questions about. You sort of have to be opportunistic because in any given scenario, there's a certain set of objects available that you can ask questions about. So the idea is ask locally convenient questions during an interactive task in anticipation of future performance gains. And the questions may not be useful for the current task, but might be useful in the future. So we did this in the context of the ISpy task. But the idea is you might ask a user a question about something that's not directly relevant to understanding what they want you to do right now, but with the anticipation that it might be useful in the future. So they might ask you, find the yellow bottle with water in it, and you say, can you show me an object that's red? And they might ask you, what the hell are you asking me about red for? It had nothing to do with what I want you to do. So one question we had is, would users be upset by this? It's more of an HRI question. You know, so we did some surveys to sort of see, were people upset if the robot, while it was trying to do one thing, would ask you questions about related things? So to get a well-formed framework for doing this, we added some context to the ISpy task. So the idea is that you're trying to pick which of these 4 objects on this table the person is talking about. But there's these 2 tables on the 2 sides that you can ask questions about. So this is the idea. So you have what we call the active test set. This is the actual 4 set of objects you're playing ISpy with. But there's 2 tables on either side with 4 objects each. And the robot, at any time, it can ask you questions about these objects. So try to help. Now, some of those questions might be helping trying to learn the words that you actually used in this task, or they might be asking about other words that they had with the previous user that we call those off-topic questions. So they can ask questions about the sides to gain information, either about the current terms or the others. And they can ask 2 types of questions. The robot can ask, you know, this binary question, like, would you use the word bottle to describe this object? Just asking, does this object satisfy this word? Or it can ask this sort of, so you ask a yes-no question about whether a predicate applies to an object. The object is one in the active training set that the robot is least confident about the predicate, and the predicate is chosen with a probability. It's sort of a sample inversely proportional to how confident it is. It's sort of picking properties that it's unsure about those objects on the 2 side tables. It can also ask a question like, can you show me an object that you would describe as yellow amongst the active test, the active training set? Obviously, you can't ask questions about the 4 objects you're trying to guess because that would be cheating. So there you can request a positive example for a predicate. And, you know, we needed this to ask some questions, because starting on, it doesn't really have much information at all. So it just samples uniformly from those that it doesn't think it has enough data to fit an accurate classifier. And then we tested sort of two styles of active learning. One is, yeah.
Sorry, so I'm curious about whether you ran into a certain issue. So if you do decision boundary sampling, I could see a scenario where the robot picks an object that's a little soft, but a little hard, and human would just be confused by the same.
Yeah, it's a standard issue with active learning. Is by picking these borderline examples, you can just pick tough examples that really, even to the human, are sort of hard to classify. And that's a standard issue with active learning strategies. We didn't do anything special. There are active learning strategies that try to make sure that you're not sampling usually what people call outliers. So, so there are active learning. I could point to some of the literature on that if you're interested. But we didn't. We did very simple on the active learning. We just did standard what's called uncertainty sampling. But doing better active learning is certainly one way we could improve this whole approach. So we compared two types of questioning. One we call the baseline, which just always asks questions about words that are in the current description that it's trying to solve in the ISpy task. And the other we call the inquisitive robot, that can ask these sort of what we call off-topic questions that can ask about other words that other users have used to describe objects, about those training examples on the side that aren't necessarily helping it solve this particular user's ISpy problem. So, say the user says, this is a yellow bottle with water filled in it, the task-oriented baseline system can ask questions about, is this object on the side table yellow, or is it bottle, or is it water, does it have water, is it filled? But the inquisitive agent can ask about any word any user has ever talked to it about in the past. So they could be off-topic. And partly we're interested in, do users get upset by that? Anyway, so now I'm just going to show you a video that we put together for this whole project. I don't know how well the sound on this is going to work. Because Coral allows you to submit video, so we submitted video.
This is a yellow bottle with water filled in it.
Did you say this is a yellow bottle with water filled in it?
Yes. Yes.
I'm turning to face table 1.
That's going to ask a question on one of these side tables.
Would you use the word bottle to describe this object?
Yes. Yes.
See. Could you show me an object that you would describe as yellow?
Watch.
I see. Could you show me an object that you would describe as bottle?
Some of the dumb questions that already asked about.
Is this the object you had in mind when you said this is a yellow bottle with water filled in it?
Full green and purple bottle.
Would you use the word red to describe this object?
No.
I see.
A transparent plastic bottle with brown peanuts inside it with a red cap.
That's a tough one. See, this is where we're treating each word separately sort of bad, because it's treating cap and red as sort of two things. It's not really connecting them together with the concept, which is another one interesting issue.
Transparent plastic bottle with brown peanuts inside it with a red cap.
Yes.
You have to speed up the humans,
So then we did a bunch of survey questions and things on this. So, and then the rounds, of course, it's learning from previous rounds when it's testing on the later rounds. But not surprisingly, the inquisitive robot did better because it's asking more questions and it's getting more information. Yeah.
So there's something pragmatically interesting in here, which is that if it points, I guess, is it guaranteed to point at something that's actually an object identifiable by the user?
Yeah, because it knows, both the human and the robot knows there's
I see.
4 objects on each table, and it's going to be referring to one of those 4 objects. So all the object identification and boundary detection, all that we're not really dealing with a lot of difficult issues there.
And also, if it asks for an example of something that doesn't exist, what is the person supposed to do?
Oh, I guess they can say, you know, there is no such object. And then we just get negative. Then we treat all the examples as negative examples of that predicate. So it does learn from that.
Oh, cool.
Yeah.
Are the objects on the side tables labeled for the robots before?
No.
No.
I mean, again, it has experimented with all of these objects beforehand, and it knows all the objects, and it has a feature vector describing all of their properties, having played with them all offline.
Including the 4 on the
All the objects are all perceptually explored all in advance. That was the accuracy. Then this is some survey stuff. It said the robot seemed to understand my description. So people actually like the inquisitive robot more. This is sort of the HRI aspect of things. So they actually thought it was sort of smarter, and I guess this asked too many questions. So this is something we have. So even, you know, it's sort of by the 3rd round for some reason it loses a little bit here, because some people think it did ask. Oh no, here it asked too many questions. But more on, people didn't really think it asked too many questions. So anyway, we thought this idea of the inquisitive robot was sort of interesting, and people actually found it more fun to interact with the inquisitive robot. Anyway, so that's a Coral paper. It's already up on our website if you want to look at it. We just submitted the final version like literally last week or something. Okay, so just to wrap up. So those are 4 different aspects of this sort of robot language project that we've been working on for the past couple of years. There's a little bit of more things that I didn't have time to talk about. One is handling polysemy and synonymy. Like I gave the example of chair could be the chair in the office or the department chair, or light could be light colored or light in weight. We did some work dealing with that I didn't talk about, that was presented at ISpy this year, just a month ago. If you're interested in learning synonymy and polysemy, not just using vision, but using multimodality data, I'd recommend that paper. We also have a paper at the IJCNLP conference, which will be next month. I had an undergraduate student hook up speech recognition to this system, but one thing we did was we wanted to use the semantic parser to aid the speech recognizer. So we have a paper, how to use semantic parsing to re-rank hypotheses from Google Cloud Speech. Some issues we haven't really fully dealt with is this issue about when I ground something. Is it something like chair where I need to ground it in the world, or I need to ground it in my database of knowledge about who the department chair is? We've assumed we haven't handled that type of ambiguity between grounding in a knowledge base versus grounding in perception. And then Jesse's busily working, hopefully even as we speak, back in Austin, on putting all of this stuff together. All the semantic parsing, dialogue learning, the grounding, all together, all working on the robot so that we can run large-scale experiments where all of this stuff is fully integrated. Right now, it's sort of like we build standalone systems for each paper, and they're really not all implemented working together on the real robot. Okay, so then to just wrap up, robots that learn language from dialogues within users, I think, is an interesting, challenging problem. We've done work on integrating both learning semantic parsers and dialogue strategies just by engaging users in dialogue. We've tried to argue that it's good to ground meanings of words not just in vision, but in multimodal robotic sensors, and that having them engage in these sort of games like ISpy is sort of a fun, interactive way for humans to train the robot to recognize these grounded natural language descriptions. And we tried to argue for this idea of opportunistic active learning. We allow the robot to ask interesting, inquisitive questions that might not be on topic about answering this user's particular goals, but will help it learn more about how to ground language in general. And people don't seem to mind to answer other questions while they're engaging in a different task. Okay. I'm happy to take any more questions.
Thanks, Ray. We have some time for questions.
Yeah, when you mentioned that you have a vector for representing each object, how is this vector created from the sensor data?
So for vision, we use a standard deep vision network. I think, I forget which one of these we use. is, but there's a lot of these standard CNN sort of feature vectors. For the multimodal stuff, we do very pre-processing on the audio and haptic signals, and again, my robotics colleagues are sort of in charge of that, so I don't know if I can answer too many details. But we actually tried to apply deep learning and CNNs to that data. But to train a CNN, you really need a lot of training data, and we just have a handful of examples. So Jesse actually spent a fair bit of time training CNNs to use this haptic data, and we just never got any good results. And I think it's only because we don't have enough training data for haptic data, because that requires an actual robot to manipulate these objects. And so I thought he had this nice adaptation of convolutional networks to this haptic data. We just never got it. We just don't have enough data to train deep nets on this sort of data. So for those we just use very simple like SVM to learn those. And then we have a higher level. It sort of learns a classifier for each modality, and then it has a higher level classifier that combines those results. We found that worked better. Rather than just giving one classifier the entire feature vector, it actually trains a separate classifier on each modality, and then trains a meta classifier to take those outputs and come up with the final multimodal decision. We found that sort of stacking of the layers was helpful too.
That's in the paper, right?
Yeah, I think that's all described in the paper. Yeah?
A question on learning language from dialogs. So the robot can draw pairs between information it knows and the ambiguous kind of way the user used. How can it predict pairs that did not appear in the training data?
Oh, well, it can't.
Okay.
I mean, obviously, you're always limited by, the training data that you've been exposed to. From clarification dialogues, you're going to pick up on certain training pairs, but certainly if you've never seen that in training, there's no way you can learn it. Yeah.
So whereas there's tons of different components like CV, NLP, and other things, why don't you just import model from pre-trained model from other areas, and then just integrate those pre-trained model from different parts into your robots?
Yeah, well, a lot of what we're trying to learn is the grounding, right? Which, all these conversational systems, they don't deal with sensory data or robots or anything else. Now, the basic language understanding, I don't know. I mean, there's only a few commands that the robot can add. One thing we're always frustrated by is from a language point of view, is the damn robot's not able to do very much at this point. So, delivery and navigation, those are the two things that we've played with. And, I don't think importing anything from Siri or Alexa is going to help us understand those. So it's pretty limited domain.
Question, Jessica?
Yeah. About the third section of work, there's 4 different cores. Did the people you were experimenting on change per core? Did you just go from one group of objects to the next group of objects with the same mid-test subject?
You're saying does the human? Yeah. Every round requires is a new set of users. I'm pretty sure we didn't reuse any users. So they're not learning from the humans are not learning from their previous rounds of interaction, just the system is. So we bring in new subjects for every round. Is that your question?
Yeah.
Yes. Is there work being done on increase the learning rate, or is there a more quantitative matrix for how much the rate of these robots can learn from this process?
You mean rates in terms of sample complexity, how many training examples they need to learn?
Example, training examples, what's the sort of learning ability, and then
like I said, I mean, there we're using just generic approaches. Like I said, the final classifiers we found, because we don't have enough training data, we pre-trained the deep feature vectors off. Everybody in Vision these days pre-trains a set of visual features on all of ImageNet or something. We certainly do that. But for the actual classifiers that we learn for these individual words, we just use SVMs because we don't have enough training data to train a deep network. It's just, in these experiments, you're just collecting handfuls of training examples. But we try to exploit all the deep network stuff in terms of the features that we extract from vision. Like I said, we tried to even do that for haptic and audio, but we just didn't have enough training data to train CNNs on that sort of data. Yeah?
Going back to the dialogue training, if you know the set of things that a user might potentially ask for, would you say there's any benefit to doing this sort of self-training or finding examples versus just going to Mechanical Turk and saying give me all the ways you might refer to the calendar, and and then taking those and just using those as
Yeah, again, I mean, obviously there are ways you can, we've tried to follow the philosophy that we want to, more engage in natural conversation rather than have Turkers label all sorts of stuff. So that's more of a philosophical difference. Certainly you could do that, but I think at least when we use Turkers, hopefully we can pay them less because the task is a little bit more fun or whatever than just producing all possible labels for something or something like that. So yeah, I mean, it's sort of a different in philosophy whether you want to go the full sort of pay whatever you can to crowdsource as much data as possible versus more this sort of online, learning through actual natural interaction. And we're trying to push on the latter idea.
So we're trying to make the robot more inquisitive. Are you also trying to make them less annoying by asking too many questions for the user and try to get their reactions and then find when they're trying to balance
so I
them?
think what you're getting at is what Aishwarya is currently looking at, which is right now we have a fixed policy for when to ask these off-topic questions. What we're trying to do is learn a better policy for when to ask off-topic questions by using reinforcement learning and just base it on reward of users accomplishing goals. So we want to do this where we don't ask a fixed number of off-topic questions, which is what this initial experiment did. But the system actually learns how can it push that boundary before it starts losing users, right? Where it actually learns from reward over many, many trials when and where to ask off-topic questions enough that it learns, because it's going to get rewarded for getting things right in the future from learning, but it's also going to get negative reward every time a user drops out or its conversations get longer. And so we really want to do reinforcement learning to learn a good policy for when and where to ask off-topic questions, and we haven't done that, and that's exactly what Aishwarya is working on right now.
Question here?
Yeah, hi.
So people are an example of agents that do this kind of thing. Does information about how humans learn from a combination of perception, dialogue, and so on give any insights into better ways to do this?
That's a big question. So again, I'm always open to learning from cognitive science research and psychological research and things of that sort. I wouldn't say that we've necessarily exploited anything, but if you have any ideas of literature there that we should be paying attention to, I'm happy to hear about it. We've been more just driving it based on our own intuitions. We haven't really looked at the psychological literature on this sort of stuff.
We got one more question in Ithaca. I'm curious about the reward signal. There's some ambiguity. Is it more proper to give a reward if the system, let's say if the human correctly understood what the robot meant versus if the human did what the robot wanted? Because that, there's extra direction of did the human want to do what the robot wanted it to do?
Yeah, so, I mean, the only time we base it on is in the ISpy. Sometimes the robot gives the description and the human identifies it, but yeah, so yeah, we're not taking into account, users' desire to help the robot or whatever. So.
Okay, thanks. Unfortunately, in Ithaca, we're going to have to disconnect because we have a class that's about to start. But Ray, thank you so much.
Okay, I'm glad you all showed up in Ithaca. Nice to see you guys.
Any other questions on this side? Okay, so let's thank you again.